Hello, everyone. Good afternoon. Today, we're going to talk about microgrids. We have Melanie Johnson here to give us this presentation. Melanie Johnson is an electrical engineer researcher in the energy branch of the U.S. Army Erdic Searle. Melanie joined the energy branch at Erdic Searle in 2008 and focuses on improving energy resilience for DoD installations with microgrids and other advanced electrical distribution technology. This work includes incorporating diverse distributed generation portfolios into microgrids and microgrid project lifecycle planning. And with that, I'll go ahead and turn it over to you, Melanie.
Hi, I'm happy to be here today to tell you about microgrids and how we use them in installations and even, why do we even bother building these things? So let's jump right in. Okay, so just to give you kind of a quick overview, what my team at Searle does is we try to look at the electrical distribution systems at our installations and figure out how we can give our installations the flexibility, the optimization, and the data visibility that they need as our distribution systems evolve into these dynamic systems whose modes of operation and capabilities change with the needs of the installation. So our research program has three main areas, the first being resilient electrical distribution systems, which typically means microgrids. So we look at, how do we control them? How do we maintain stability? We have an emerging research effort in how do we get them to analyze themselves, which I think is really cool. We have a pretty deep program in power sensing where we have these sensors there. We power system geeks would say they are on the grid edge, but they can be put throughout a distribution system, and they help us examine power quality in the system. We can use them to some extent to perform condition-based maintenance and figure out when equipment is going to fail before it fails. And they give us a way to check the system status and create kind of a validation channel if you think that other control systems and monitoring systems have been compromised, like from a cybersecurity standpoint. And finally, we look at interoperability. We had a big effort a few years ago to develop a tactical microgrid standard for how microgrid control systems communicate with attached equipment, and we're looking at how do we bring that into the installation space. We look at how do we develop digital twins of these distribution systems, and how do we bring that all together where we can look at it and talk to it in one place and get all of our different infrastructure control systems talking together at the same time. That's kind of our research side. The other side of our team performs engineering support. And what that has been in recent years is that we're supporting ERSIP programs that are deploying microgrids to our installations. So we look at how they're designed. We try to help as much as we can with cost estimating, even commissioning and planning for sustainment. In the last year, we've worked with Navy to develop the microgrid installation energy or microgrids for installation energy resilience UFC. It's in its final form. It's out staffed for signatures. So hopefully that'll be a useful tool moving forward. That's just a quick overview of what our team does and what our the whole scope of our work. We're going to jump a little more in depth into like what are microgrids and why do we build them from here on. All right, so if you've been around installation energy as long as I have, you've seen some trends develop starting around 2005, 2007. We started to see a real push at our installations to deploy renewable energy and renewable generation. And when we did that, we put a bunch of systems out there, and that's great because they do offset our consumption from the grid, but they didn't enable us to island from the grid. They didn't really deliver the energy security that we had planned for or intended to have because they weren't able to disconnect from the grid and operate in an islanded mode. And this is where you really see the genesis of the idea of having microgrids for our installations, where they can use all of those resources that we've put out there, island from the grid, and serve critical loads. So just to give you a sense of where have we gotten to, this is sort of where we ended up after the first generation of energy security projects. And now as we try to move towards this mindset of energy resilience, we want to be able to connect our different infrastructure control systems. We want to be able to have these systems get authorities to operate and be accredited for our cybersecurity standards. We want to be able to use our resources in very flexible ways to serve loads as we need them, and we want to be able to see everything that's happening, which unfortunately isn't the case right now. So why are we building microgrids at our installations? And it really boils down to the fact that every mission we have depends on electric power. But delivering electric power to our critical loads faces increasing threats from a variety of places, whether it's from severe weather that we're seeing, from climate change that induces more frequent or more severe weather events. There are cybersecurity attacks. We have aging infrastructure all over the place. This is one of my favorite pictures because this is one of the hooks that caused all the wildfires in California. That's what they look like after they've been up on transmission lines for 100 years. And we have increasing demand throughout our system. And this is, this is what we see at our installations, but this is also what we see throughout the commercial bulk power system, the same threats and having to respond to those. So the other facet of this is that our requirements in the Army for our electrical distribution systems and all of our infrastructure really outpace what we see in the commercial environment and what we see in our existing capabilities. We're demanding higher power quality, higher reliability. We are integrating distributed generation resources, meaning just things that aren't like a big power plant that's somewhere far away from you sending power along power lines. We're putting the generation out into the distribution system. We require much stronger security postures from a cybersecurity perspective, as well as from like a physical security perspective. And we're now seeing pressure to integrate electric vehicles. So all of these things push our infrastructure systems into the space that we're not getting to in the commercial sector. And we started to see all of this recognized more clearly in policy in the last few years. So if you, those are just a few of the pieces of policy that are sort of governing this movement and this pressure for our installations to move to these systems. So what microgrids do is effectively they enable us to have better energy resilience, right? They improve reliability. When we lose power from the grid, we don't have to rely on one single generator supplying one single load. We can use the whole portfolio of generation we have at the base to serve the whole portfolio of the base's loads. They give us better endurance in that situation. So rather than having one diesel generator and its fuel tank serving your critical load, now I have the flexibility to use renewable solar power when it's available. We can use energy storage to extend our availability, and we can run our generators in more optimal set points so that our grids last longer when we're not connected to the commercial system. By that same stroke, they give us better sustainability, right? We can use our renewable energy sources and reduce our fossil fuel consumption. So that helps us move towards that goal of decarbonization, but also, as we just talked about, it enables us to run longer. In a perfect world, these systems also interconnect and talk with whatever smart grid capabilities are available in the commercial system, allowing us to reduce our costs and generate revenue streams. So that's a somewhat unrecognized benefit to date, but we're working on solutions. And finally, all of the additional control systems and data that we collect in this system gives us better visibility about what's happening in our distribution systems when they're operating, whether we have enough load, if there's other conditions that we need to consider, and how we allocate our available power. So at the end of the day, what microgrids are really doing for us is making sure that we have a fallback position so that as our situation degrades and we lose commercial power, maybe we lose our central generation plant, and then we lose our, our interconnectivity of our microgrid where it shares loads, we always fall back and fall back and fall back so that we can keep our most critical loads on. Okay, so we've talked about why we need microgrids at our installations. From here, we can start to talk about, well, what are these things? Well, now we've established that we need to build them. So what do they contain? So this is sort of pulled from the draft microgrid UFC. So you can see the number down there if you want to look it up on Whole Building Design Guide. But a microgrid is, there are lots of definitions that float out there. Generally, you will see some reference to a microgrid containing multiple generation sources and multiple loads. So this would disqualify that single generator connected to a single building, right? We have to have more than one of both. So in the UFC, it calls out that the microgrid has to be able to island and use multiple generation sources. So you'll see there's there's a battery and a generator here. There's a central utility plant here, and now we have some large-scale renewable energy storage and generation out here. The UFC defines a microgrid as having a defined boundary. So this microgrid system exists maybe on this one electrical feeder in the base. It has a clear point of connection with the utility, and everything within it happens within that defined boundary. Our microgrids have to be black start capable. That means if the power goes out and the microgrid doesn't, if everything has gone dark, there's a complete power outage, microgrids have to be able to start from that condition, which is, in some cases, a fairly tricky capability to provide. The UFC also requires that the microgrids meet mission load requirements to meet resilience requirements. So it's just sort of saying you have to have some reason to build the microgrid that coincides with your reason for needing energy resilience. The microgrid control system has to be able to perform system balancing. That means that it has to make sure that generation and load are equal at all times. It has to perform that function. That's generally something that's performed at the bulk power grid level, but we have to bring it down into the system to make it all work. And finally, the UFC calls out that we have to have that fail-safe back to a pre-existing backup condition. So if the microgrid fails to form, we want to see all those other backup systems come online and support the critical loads as they did before. So this is slide is a little bit cluttered, but the idea is here to kind of show you how a microgrid moves through its different operating conditions. So under normal conditions for most microgrids, the installation loads are receiving power from the utility. If we have an unplanned outage, everything goes dark. We call this a break before make microgrid. So everything goes dark, UPS is operated as intended, spot generation comes on as intended, and then the microgrid begins to form. So that's where we encounter microgrid black start. So the microgrid will have some preset procedure that it initiates when the power outage is when the power outage occurs to restart power generation within the microgrid and supply our loads. And so once that procedure completes, we've moved into islanded operation where the microgrid is now providing power to our facility. Most of our microgrids are going to have the ability to do this on purpose and instead of only experiencing an unplanned outage. So in that condition, what we like to do is bring microgrid generation online and operate it in parallel with the power grid. And then we have a set procedure where we increase our generation from our microgrid sources until we're not pulling any power from the grid, and then we disconnect and we've entered islanded mode. And in this circumstance, we don't see any outage at all. Barry, I see your comment about the electric toilet. There's a whole research group at Searle that does waste to energy. So the electric toilet is to recognize their efforts at using our waste streams to generate electricity and make our installations more sustainable. It's one of my favorites. So once we've entered islanded operation, our next move is going to be to return to grid power. So it's kind of the opposite of this arc over here, where we reconnect to the grid, we slowly ramp down our microgrid generation so that we've returned to grid power, and then we disconnect the microgrid and we return to our normal operating conditions. So a couple notes. For some microgrids, parallel operation is normal operation. Typically, if there's a central plant or something like that on the installation, sorry about that, that's where we would find that. I'll also note that in an unplanned power outage, some microgrids do have some limited blinkless transfer of loads. This is usually provided by a large energy storage unit that carries some portion of the microgrid load through that blink where other backup power hasn't come online yet. So for some loads, that's the UPS capability, but for others, it's in another microgrids, it's a specific feature. Okay, so the next part, I'm going to walk you through what happens when we start to implement a microgrid on an installation. So this is Camp Resiliency. And at Camp Resiliency, they've put a lot of effort into putting generation and renewables and energy storage at the base already. So we've walked into Camp Resiliency and they've already done a lot of work. In some of our ERSIP projects, this kind of development of resources happens in the same project, in the same effort as implementing a microgrid. But since we're only talking about the microgrid part, Camp Resiliency, they've already done all this. So you can see that there's some central backup generation that they've installed. Their most critical loads still have generators locally connected. They've installed some large-scale solar as well as some large-scale energy storage. And they have some limited SCADA capabilities in their main substation that's connected to the grid. So the first step at Camp Resiliency is that we really want to use that existing generation at those critical loads. It gives us a little more flexibility. It'll give us a little more resilience to have additional generators able to provide loads to the installations. Excuse me. We're also adding a sexualizing switch to kind of give that endpoint boundary to our microgrid that's on this feeder. So we could assume at Camp Resiliency, maybe there's additional loads, maybe on a looped feeder going this direction, but we're going to add a switch here and call that our microgrid boundary. The next layer that we have to add is organization control for our generation resources, as well as our point of common coupling up here with the utility. So what these controllers do is they ensure that when we connect spinning generation, they connect synchronized, and they also will perform the very basic load balancing between the generators. So they'll ensure that the big generators provide the same percentage of power as the little generators and keep that all nice and balanced between them. This is also what enables us to sync and do that seamless transition with the grid. The next layer of control that we're going to add is we're going to extend that SCADA system down the feeder so that we have visibility as well as remote operation capability for all of the sectionalizing switches along the feeder. We use this during black start to slowly walk power down the system to limit our exposure to that cold load pickup and the inrush currents that occur when you re-energize an electrical system from dark. It helps us make sure that we maintain stability. It helps us let any transients settle out. In some microgrids where we have more like energy storage, we may have to energize a part and then wait for our batteries to recharge before we energize the next part. This also gives us good controllability and visibility while the microgrid is operating. And then finally, we get to layer on a microgrid controller. The microgrid controller's job is to optimize and perform what we call economic dispatch, so picking the best generation resources to meet the load. That's its primary job. So it's going to integrate with all of those other systems. It's going to talk to our SCADA system. It's going to talk to the synchronization controllers. It's going to talk to the generator controllers. It's also going to interface with the PV inverters and the charge controllers on our energy storage. So it's the link that brings all of this together and makes it all work as a single system. So there's our final microgrid. You can see that to do most of this, we've actually added controls more than we've actually changed the distribution system. So kind of an interesting, you have to understand the distribution system to do it, but then when you dig in, you're mostly doing controls work. So if you work in controls, this figure probably looks very familiar. It's very consistent with a lot of other figures that are found in various standards and even like the control system UFC. So down here at the bottom, we have the equipment. This is the physical equipment that's working in the microgrid. We have onboard or local controllers for each of those pieces of equipment. We have some system controllers that interact with these. The SCADA system I kind of split between because it's kind of all the things. And then finally at the top, we have that tertiary optimizing and dispatch controller for the microgrid. Okay, so this is kind of the end of that example. What do we do when we build a microgrid and an installation? From here, I'm going to talk more about our design philosophy and how do we approach these projects as we develop the concept and then design and then think about how we're going to move that project through its whole life cycle. So a microgrid project has a life cycle like any other, and like any other project, if you plan for maintenance and sustainment in design, your project will have much better outcomes. what we found in a lot of our early microgrid demonstrations is that they weren't sustainable. The bases couldn't maintain them because of a lot of design choices that we made, whether it was having everything exist on a closed restricted network, using novel technology for generation resources, or imposing artificial constraints on the design, which we'll talk a little more about in the next slide, I think. Yep. So from those demonstrations and our early work on microgrids, these are kind of our key design aspects that we developed. First and foremost, always define and document the objective of the microgrid. And the objective of the microgrid isn't to be a microgrid, right? It has some purpose, it has some mission. It's going to add energy resilience and provide backup power to some set of critical loads. And part of this should also be for how long, and if you can, under what threat? Are we addressing a weather threat? Are we addressing a cybersecurity threat? What threat are we addressing with this microgrid? It can help us make better choices as we move through the design process if we have clearly defined what is the microgrid for and why are we putting it here. We have to limit our artificial constraints. So in many cases, what you'll see in a microgrid is that for a political or it's a priority, but not necessarily a technical priority, that we use some specific thing at an installation, whether it's an existing solar array, an existing generator, or perhaps a demonstration project that's already in place. These days, what I'm seeing is saying we have to use these third-party owned assets. Those can be really tricky to work through. It can really limit the choices you make in design. It can constrain you extremely on like the legal and agreements front to make all of this work. So we try to be careful to only make those choices and limit ourselves when we absolutely have to. So in the case of like the third-party owned assets, that's not something we can avoid, but we want to make sure that we want to select those carefully and make sure that we don't promise to use things that are really pretty much impossible to use. We should never harm the installation's current backup power posture. So do no harm to how their backups currently work. Make sure that they have the same reliability and functionality that they had before we built a microgrid. As noted before, we have to make maintainable choices, right? We might pick equipment the installation already uses. We might install controls or switches and things that we already use at the base to make that maintenance and sustainment easier long-term for the post. And finally, we always need to define the ConOps. How does the microgrid work? What are its operating modes? How does it move between the operating modes? Where is a human required to make a choice and to flip a switch versus what is automated? Who has to be notified? How do we make those notifications? All of that should be documented somewhere as a procedure. I see lots of questions in the chat. We'll go back to them. I think I'm almost at the end, so I'm gonna go to the end and then I'll answer all the questions. In a little more concrete way, this is how ERSIP microgrids are currently being built. Microgrid conceptual designs come from a number of places. They are proposed by the installation to the ERSIP program as a draft 1391. That 1391 gets routed to Huntsville, where they perform validation of the 1391 to ensure that the project is feasible and that the cost estimate is reasonable for the work proposed and there's no gaping holes or gaps in what's been considered in that microgrid design. If that microgrid is selected for funding by the ERSIP program, it then moves into design with Louisville District with support from Huntsville. After that, we move into construction, testing and commissioning, and sustainment, just like any other construction project. This is my squinter of a chart. I'm not going to walk through all of this, but this is a very detailed look at all of the different things we're considering as a microgrid project moves from design into acquisition into design with a contractor and construction. There's a lot of different pieces and stakeholders that should be involved in that conversation. And if you get involved in one of these projects, I hope that this chart kind of helps you frame your thinking how you approach the different stages of the project. So after the microgrid is built, it has a few special considerations. One is that it's a system of systems. And so its ongoing testing plan and maintenance has to consider that each of those systems needs to be tested and maintained individually, as well as the integrations between them. So that's one of the key things we look for in the testing and commissioning plan, is that they're going to test each subsystem and then each integration, and then slowly build up to a whole system test. And no one will change my mind that a black start test is a requirement for commissioning a microgrid. In fact, I will go so far as to say you should black start test your microgrid at least once a year. Otherwise, it doesn't work anymore. We need to provide training to both government personnel and contractor personnel who will be working with these microgrids. And we can't neglect training and maintenance on how to maintain the controls and information systems that are underpinning all of that capability. And finally, our documentation has to be good. We need to make sure that we've provided all of the as-built, and if there is a way to easily expand the microgrid, that's been documented in that documentation. So we've talked about how we're doing it now. This is my reading of tea leaves, looking in the 8-ball to tell you what are the problems that we're going to encounter next. We've seen requirements for vehicle electrification, building electrification, decarbonization, all percolating to the surface right now. And that's going to change the demand profile of our installations. This figure here is just notional. It's not supported by data. This is just me imagining what the situation could evolve into, where we have increased electrification that's going to exceed what we planned for our microgrid capacity, even our distribution system capacities. We will see charging peaks, particularly for tactical vehicles, where we're looking at, megawatt demands to charge a vehicle in 15 minutes for some of the tactical vehicles. So it's really going to change what our installations load profiles look like, from this nice, nice wavy looking that we're used to something that's a little different, I think. In doing all of that, we will also have to consider how we're going to decarbonize the generation at our installations to meet our resilience requirements and keep the lights on for 14 days without the commercial grid. And finally, as we add control systems, we are expanding our cyber attack surface. So we have to consider that and make sure that all of these systems are well protected, well monitored, and well maintained from a cybersecurity standpoint, as well as a operational functionality standpoint. This is my research group's projection of all the different capabilities and technologies that we will need to address these emerging problems. We try to cover as many of them as we can, but some of them are still things that we will address in the future. But just to give you a sense of where we see solutions coming from. This is a more in-depth look at the research program. I'm gonna skip through this and say that I think we're probably good. I saw a lot of questions popping in the chat. Let me see if I can bring the chat up on my screen. Here we go. Okay. 1 second while I scroll to the top. We already talked about the electric toilet. So on the question of does the local utility or grid manager have any say in how the controls work? That's a fairly complicated question, so it depends. In general, we're trying to operate without the grid. Excuse me. I'm going to mute and clear my throat, and I will be right. There we go. That's better. So right now, because of cybersecurity concerns and the way that we get the way that we move through the RMF process, we can't have a connection between the utility and our microgrid control system if it's on a government network. There may be some flexibility to make that connection if it's on like a privatized utility contractor's network, But even that can be kind of a fraught relationship. So what you'll generally see is at the point of common coupling, the utility company will have their breakers that they control to either let us be connected or to cut us off, and we have ours. And we each operate our own set, and that's the extent of the relationship at the point of common coupling. I think that covers the PGM questions, unless there's any follow-up to those. So on the sole source question, the biggest sole source question we have in most of these is whether or not we can allow the privatized utility contractor to do the design and construction, which is my understanding is at this point in time, it's basically technically illegal for us to do that. So there's a lot of questions being answered at high levels in USACE and the Department of the Army about how we might work through that and whether or not we need Congress to change laws to make it possible. As far as speccing equipment, we try to avoid saying, you know, thou shalt use a specific model, although with some of the privatized utility contractors, that's what they're looking for. We try to make sure that we're consistent with the capabilities of the equipment that oh my goodness, that the installation already has. Excuse me. Single building solutions. So single building solutions are actually considered. There are buildings out there that are and single facilities that are trying to use microgrids, like in the sense that the building is multiple loads within it, and then we have multiple generation sources attached to the building. The problem here is that that's actually a lot more controls for a lot less capability. So it doesn't actually take me that much less control, that much less integration, much less maintenance to do like a low voltage microgrid like that than it does to do like a whole medium voltage microgrid. So it depends on if you have like a single facility that has maybe rooftop solar and energy storage already co-located, you can sometimes work that out. But our life cycle cost analysis generally points us to medium voltage microgrids, not low voltage microgrids. And small scale nuclear reactors, I mean, I think the answer is yes, they're considered, but that is a much higher level decision and consideration than folks who are like me who are trying to implement microgrids. I know there's some like classified side programs in how to do small modular nuclear reactors. So, I mean, I think it could be a great solution, especially for our larger bases and with an eye on requirements to decarbonize. Right. Anybody in the chat isn't happy with my answer, speak up now. We know what else I can answer for you. So large-scale energy storage. Most of what we see out there is going to be lithium-ion batteries, and it's getting more cost-effective. So usually in the several megawatt class. So remember, energy storage is always specified with two numbers, right? It's power output. So there's the number of megawatts it can discharge and charge, and then there's how many megawatt hours it stores. So depending on the installation, you'll see, I don't know, the smallest ones I'm seeing these days are like 1 megawatt hour to try to accommodate larger photovoltaic arrays. So it's getting more cost effective. And yes, they do pose a fire hazard, and you have to comply with. I assume that's the UFC that says I have to be 100 feet away from a building or something along those lines. And it's very tricky in some of our smaller, more crowded installations to find somewhere to site a large lithium-ion battery. But yeah, so the cost effectiveness, it kind of depends on a lot of factors about the installation. concur, Daniel, that there are lots of challenges in siting those batteries. Yep. There's also utility scale energy storage UFC.
Well, I think that goes. Most of our questions have been answered, and it's kind of slowing down in the chat. So,
Okay.
Melanie, I just want to thank you for putting this presentation together, and this was a great webinar. I definitely learned something. And with that, I guess we can stay for a little bit longer and see if anybody pops up
Sure.
with other questions. The other thing that I wanted to mention, two kind of announcements. I did make a mistake with the schedule, and I haven't sent it back out. I'm going to utilize the participants on this meeting and send the new schedule to those, because typically we invited over 700 people, and we typically average between 120 and 170 for each individual one. So I don't want to send it back out to everyone that I initially invited. The second thing is, I have not posted it to YouTube. The link that was in the initial invite was to last year's webinar series, which we were going to add to. But since I've had some technical difficulties with my computer, I've posted them to the sustainability teams site because they're very large files. I will put them on YouTube, or the ones appropriate that we can share on YouTube after the last webinar is done. The webinars that for the schedule is next week, we are doing EV, electric vehicle charging facilities. I believe that's the new correct term. We're doing that next weekend. And then after that, we're going to have OSD talk to us about new policies that may come out. We've just received a electrification policy, but we'll have a little bit more information from them on the other policies that will come out. With that, we'll stay on a little bit, and we'll see if you have any other questions.
There are a couple more. I am not an expert on lithium-ion storage systems, so I don't want to guess at their efficiency. I think they're fairly good, like in the 70 to 80% range. But it's not my area of expertise. David, to your question, I think we run into each other a few places. If you don't own the distribution system, you have to wait for the people in Washington to figure out how they're going to handle those. So that's unfortunately where the utility privatization contractor and microgrid situation sits.
Right. I think that about covers it. If anybody wants to email me more questions that we can discuss, absolutely send me, and we'll get you the correct answers.
Curtis, I see your question about vehicles. We've done pilots, we've done demonstrations of vehicles providing power to the grid to basically use them as batteries on wheels. I think there's a lot of